0. Which is very important. Proven by the
Okay, I think that's pretty good.
What do you do on it?
From the packet, would you look at number 2 with me? Thanks. Now, I know that some of you, I can tell, almost all of you are working on your lab. Put the lab aside. I'm going to try to get through this and have 15 minutes or so at the end of the hour for you to work on that. And I will tell you that I don't know what you have going on after school today, but Mr. Hell and I both, almost right at the end of the school day, we have to rush out of here. We have a meeting to go to at central office. So, no, you can, but it doesn't matter what time you turn in because we're never going to know. We're going home after the meeting. So if it's 5 o'clock when you turn it in, we'll never have known. We'll just get those labs from the shelf tomorrow. Okay? I hope. All right. So some of this we did yesterday. We're going to go through the whole procedure again today. When we're given data like we're given in number 2, where you have concentration of reactants versus the rate data. In number 2, there's just one thing that's different from number 1, and that is that we have 3 reactants in number 2. There's not just 2 reactants, there's 3. So that means that the data table is going to be a little bit more filled up with the varying concentrations of 3 reactants this time, and then the rate is given. We're looking for steps in which, not steps, but trials of this reaction in which the 2 of the reactants are held constant and the other one is changing. So if we want not the concentration, but the order of A, we'll use trials 1 and 2. Because when you see, B is held constant from trial 1 to trial 2, and C is held constant from 1 to 2. The only thing that's changing is the concentration of A. This may not be easy to see, but as A goes from 0.1 to 0.3, A is tripling its concentration. What's happening to the rate? Well, everything else is staying constant. A triples, and the rate does what? Can you tell? If it's not clear, then grab your calculator and divide the rate from trial 2 divided by the rate from trial 1. Go ahead, I'll wait for you. No, look at the power on the 10. That matters. Oh, that's small too. Yeah. It could be. Yeah. But you know, I'd give you nicer numbers than that because it's not very easy for people to look at that and see that the rate is going up by 9. When you take the second rate divided by the first rate, it's a factor of 9. So, now check this out. If A triples, and that causes the rate to go up by 9, what does that mean the order of A is? 2. It's second order, right. Whatever change happens to the concentration, if that change squared happens to the rate, that means it was second order. And that's what happened here. The rate went up, so the concentration went up by 3, and the rate went up by 9. So that means A is second order.
So it's quadruple?
Well, I had told you in the notes that if A doubles and that causes the rate to quadruple, which quadrupling is 2 squared, right? So if whatever you do to the concentration, that change squared happens to the rate. In this case, we tripled the concentration, and that causes the rate to 3 squared. 9, it goes up by a factor of 9. That's how we know what the order is.
Okay.
Yep. But we do these as examples. Hopefully it's not so, I mean, you'll have seen all the different scenarios by the time you do the test. So yeah, A is second order. What about B? We're going to use trials 2 and 3 for B because A is held constant and C is held constant in trials 2 and 3, but B is doubling. When B doubles, what happens to the rate between trial 2 and trial 3? Nothing, it stays the same. So that means B is 0 order. Oh, those are easy. For the order of C, we're going to see if we can tell from trials 3 and 4. A is held constant, B is held constant, and from trial 3 to trial 4, C goes up by a factor of 4. What's happening to the rate? It's going up by 4 as well. So what's the order on C? It's first order. Yep. Because the concentration of C goes up by 4, and that causes the rate to go up by 4. That's first order. So if whatever change you apply to the concentration, if that same change happens to the rate, that's first order. You good?
Wait, for the trials 2 to 3, the order of these, yeah, like I thought if it stays the same, is it always the 0 order?
Yeah.
Like, didn't the order of C, oh yeah, being multiplied by 4.
Yeah, the concentration of C went up by 4, and it caused the rate to go up by 4. That's first order. All right, so the overall order of the reaction is just all these added together. That's a third overall order. I had told you yesterday that we're going to look more at what the order really means. It does have very much to do with mechanism, but we'll talk more specifically about that tomorrow and try to make sense of it. Now, once we've done that work, all our hard work is done. Then it just says in B, what is the rate expression? That's the rate law. Well, I've already started it here. Rate equals K times each reactant concentration to its power. So it's A to the second power. You don't even need to put B in there because it's going to be 0 power, times C to the first power. That would be the rate expression, also known as the rate law.
Second order.
Yeah, we decided A was second order. Yep. And the order is what power it goes into it in the rate law. Now, for part C, calculate K. I showed you yesterday how to calculate K. Calculating K is really easy. Just choose one of the trials and plug the rate and the concentrations into it. The only thing you won't know is K, so you solve for that. So I always look for the trial that has this numbers that look the simplest. In this case, I'm going to choose trial 1 because all the concentrations are 0.1. So the rate is 2.5 times 10 to the negative 4th molarity per second. And that's equal to K. So for finding K, I just take the rate law, this rate expression that we found, and plug all the numbers into it from one of the trials. There's the trial 1 rate. The concentration is 0.1 molarity of A squared. Remember, A gets squared. And then B is to the 0 power, so we leave it out. 0.1 molarity for C to the first power. So the math on this is super easy. On the right side, K is being multiplied by 0.1 times 0.1 times 0.1. That's 10 to the negative 3rd power. So when I divide out that 10 to the negative 3rd to get K by itself, this number's got to be divided by 10 to the negative 3rd. That gives us 2.50 times 10 to the negative 1st. See how I did that? That number out multiplied by the K is 10 to the negative 3rd. So just divide that out to solve for K. That number divided by 10 to the negative 3rd is that. What's the unit on K?
Seconds.
1 over
30 times second.
more than that.
1 over.
You got 3 molarities over here.
Squared.
Yes, and only 1 molarity there. So when you divide out the 3 molarities, 1 is going to cancel with the one that's already there. It's going to be 1 over molarity squared seconds. Or if you insist, hertz over molarity squared.
Really?
I know, yeah. Anything about this that we should go over? We're going to do another similar example next.
Wait, what about D?
I'm going to skip D because when it says determine the initial rate of B and C, they didn't say what trial they were talking about, so we need to know which trial. I'm just going to skip it. We're going to do a question similar to that next. Let's go to, flip the page in the packet over to number 5. Go to number 5. That's the next one. I warned you this was going to happen. Our luck has run out. I told you that finding the order of the reactants is real easy as long as something is held constant every time. In number 5, you have 2 reactants. There's ClO2 and there's fluorine. Take a look at the fluorine column in the data table. What do you see?
It's always
It's never held constant, is it? That's a little bit of a rub. A rub. So we're going to have to do one extra step to figure out the order of ClO2, because fluorine is never held constant in any two trials. Why would they do that? That always just makes me wonder. If you're doing an experiment trying to find what the order of the reactants are, wouldn't you always fashion your experiment to make sure that you have only one thing changing in two of the trials so that you can figure out what the orders are easily? But that makes it so it's a challenge for you.
Wonderful.
Did I
think.
Did I run out of storage? Oh man, I thought I had a bunch. Oh, low battery. Okay. Keep watching, guys. Thank you. Fine. Okay, so here I'm going to do this up on the board so you can see what I'm talking about. If you're still trying to work on your lab, set that aside for a moment. Let's do this together. This is going to be the biggest problem that you'll have with rate laws. Rate laws are generally very easy. This, though, is not. I'm not saying this is terribly difficult, but it is something extra. So take a look. In trials 1 and 2, the concentration of ClO2 is held constant. So we can easily find the order of F2. F2 looks like it's going up by a factor of 4 from 0.1 to 0.4. And what's happening to the rate? Can you tell from looking at it? It's quadrupling. Yeah. So the concentration quadruples causes the rate to quadruple. What's the order of F2? First order. It's first order. Because remember, first order means whatever change you apply to the concentration, that same change happens to the rate. The concentration went up by 0.4, not by 0.4, it went up by 4. The rate went up by 4. That's first order. So I'm going to write above F2 first. We know that F2 is first order. Okay. So now, every other set of trials, something is changing. Both reactants are changing. Since we know that F2 is first order, though, that's going to help us. I'm going to use trial 1 and trial 3 to try to figure out the ClO2 concentration, not the concentration, but the order. If we know that F2 is first order and its concentration doubles, everybody look at this. If F2's concentration doubles, what should that do to the rate? It should double it because we know F2 is first order. Now this one is changing too, but just the fluorine is doubling, and so what I'm going to do is I'm going to correct the rate. The rate is 2.4 times 10 to the negative third. Because of the change in F2, now right above the arrow I'm going to write F2. It's hard to read, but that's an F2 up there. Being first order and the F2 doubling, that causes the rate to go up to 4.8 times 10 to the negative third. That's just from the F2 changing. Now, look at the ClO2. The ClO2 also doubles. It goes from 0.01 to 0.02, from 1 to 3. Now I'm going to take this corrected rate and see how much the ClO2 influences that. So when the ClO2 doubles, what's happening to the corrected rate from 4.8 to 9.6? It doubles as well. That means the ClO2 is first order. So again, I'm going to give you a replay on that. I knew that F2 was first order. So when that doubled, I know that that should double the rate. So that I went from 2.4 to 4.8. I corrected the rate based on what the F2 did. Then I'm going to go from the corrected rate to the final rate. When ClO2 doubles, from there to there, it looks like the rate is doubling. That means that ClO2 is also first order. So there's just that extra step of correcting the rate based on the one whose order you know. Yeah, Colby?
Wait, how did you determine order for F2 again?
F2 was easy because in the first two trials, this was held constant.
So you do.
So this went up by 4 and that caused the rate to go up by 4. That means it was first order. Okay? So find the one you can find the order of first. In this case, it was the F2. And then find 2 trials which look easiest. I would say trials 1 and 3 look easiest. So that doubles, you double the rate because you knew F2 was first order. Then when you see this change, that's doubling. See how the rate of the corrected rate changes as we go from trial 1 to trial 3. That doubles it as well. We're going to do another example just like this next. So I'll give you a chance to try that out too. But the rest of this is more of the same. In part A, it says write the rate law expression. So now that we found the orders, that's simple enough. Rate equals K times ClO2 to the first times F2 to the first. And in B, calculate the numerical value of K. Oh, well, this is easy again. We've been finding the value of K. Choose any one of the trials. Which one you want to use? The first trial is the easiest one, yeah, because you've got all these 0.1s in there. So the rate equals is 2.4 times 10 to the negative third molarity per second equals K, that's what we're trying to find, times 0.010 molarity to the first times 0.10 molarity to the first. I'm just recopying the rate law but plugging the numbers into it, except for the K, which I don't know. I can solve for it now. Doesn't matter what trial you use, the K is going to be the same value. You get the same. Don't poke it. Okay, can you do it without a calculator? This is 10 to the negative second times 10 to the negative first. That's 10 to the negative third. Oh, we've done this one already. This number divided by 10 to the negative third gives me just 2.4. And then what's the unit? You're not allowed to answer anymore. You got 2 molarities over there and 1 there. So they don't totally cancel out, do they? It's 1 over molarity second. 1 over molarity second. Good? So that's our K value. 2.4 inverse molarity seconds. Now in part C, C is like the questions that I just skipped over in the last 2 examples where they're asking us for one of the rates. Take a look at C. In experiment 2, what is the initial rate of decrease of F2? All right, now I'm going to have to, yeah, that's good. How do we answer that? In experiment 2, what is the rate of decrease of F2? We're given the concentration of F2. The way we answer questions like that is, look up here, at the top of the rate column, right here, they always will define how they're finding the rate. The initial rate of increase of ClO2F. So they're measuring the rate based on how fast that is being made. The question down here is, how fast is F2 getting used up? So if in trial 2, and it's asking us in experiment 2, if the product is going up by 9.6 times 10 to the negative third, how fast is F2 getting used? What's the relationship between that and that? It's a 1 to 2 ratio between those two. Every time one of these gets used up, 2 of those get made. You agree with that? Based on the coefficient ratio. So these questions, we'll always just go back to the original overall balanced equation and just use the coefficient ratios. Whatever change happens to that one, only half the change is going to happen to the F2 because of the coefficient ratio. So since the ClO2F is that rate, the F2 is going to be changing by 4.8 times 10 to the negative third, half of that. And I would just write it like this. Half of 9.6 times 10 to the negative third. From the coefficient ratio. So that would be 4.8 times 10 to the negative third. See how I got that? We'll do an exercise like this in the next one too. So I'm going to skip D. There's something about D that I want to just wait until tomorrow to do. So we'll do that one. I'm going to come back to that tomorrow. Would you now turn in your packet, go back to number 4. And I'm going to give you about 5 minutes. Would you try to do number 4 on your own? Or with somebody around you? I would suggest either do it and then check with somebody else, or just walk through the whole thing with somebody around you and see if you can get that.
Wait, is like the initial rate of disappearance like when we get just now? Like 4.2.
Yeah. The rate that you're given here is how fast the product is being made. The question in C was, how fast is that getting used up? Well, you just use the coefficient ratio. It's a 1-to-2 ratio. However fast that gets made, that goes half as fast.
What did you lab? Why did you do lab? You can't work on anything. Total on I'm gonna ask questions about things in my efficiency. Making it 3.24. Order that.
It's asking me to
Which case it's later.
I'm not doing that.
What is this, an AP class? This is an AP class?
This English 10.
Exactly.
Even what you get on your long run. 96. 48 out of 50.
95 out of 100.
Oh, you yep. Student teacher or okay,
What was your
fine.
so big. Dude, no, a 5 was a 90 for us. That's more than 80. They graded harsher than other people. That's kind of messed up. Oh, late now it's like this.
That's weird.
I was just right behind. Find the exact value. You have to actually find the right constant. 324 is a nice number, right?
You even stop doing this complaining.
27. It's because 01012 and 1910.
You have to.
Wait, you need to talk about money for color.
I need to calculate or find the order. Wait, why is it 6.42? It's a weird number.
Yeah, it's approximately plus.
Oh, it's approximately. You see the approximate. Okay.
These guys are bad at math and actually.
Oh, I understand.
Because they were asking about
Were you able to come up with the rate law?
experiment
The NO being second order? Could you come up with that?
Oh, no.
Nice.
I thought I was
Good.
so close.
Good, cool. This is another one where this is never held constant. So we have to figure out its order, which is not hard. Use trials 1 and 2. It's first order. Unfortunately, you don't get exactly twice as much, but don't be thrown off by that. This is experimental data. Yeah, it's not exactly.
0.99.
Yeah, but it's close.
Haha, you're so funny, Reed.
So we know that BR2 is first order. Use trials 1 and 3. BR2 gets cut in half. So because it's first order, you would cut the rate in half from trial 1. Then the NO doubles. So how does this corrected rate from 1.62 change to 6.42? It's going up by a factor of 4. So that's second order.
Oh, I did it another way. It was like, because I did
Oh, I got
the NO2 since it remained unchanged for the first and second experiment.
Yeah.
Could you solve for order doing that?
For the NO's order, how did you come up with second?
Well, because it doubled. Well, it was close. That was
Yeah, this one doubled, causing that to double. So that would be first order for BR2.
That is second. Okay, thank you. Yep.
So in A is where you do the stoichiometry. It was a 1 to 2 ratio. The rate of the reaction, this set of data, is based on how fast NOBR is showing up. That's twice as fast as the BR2 gets used up, so that's why, again, I cut that one in half. Because it was 1 BR2 makes 2 NOBRs. That's the 1 to 2 ratio. The rate is, once we find the orders, is easy. And then the K value, I got about 105 or 106 for the K value. Anybody have any questions about any of that? Now, I would like to do the last one we did about that mechanism.
You subtracted 6.42 minus 1.62 as on there before? Or what was it?
Right here?
No, at the,
Up there?
For B, yeah.
No, because we knew that BR2 was first order, that from 1 to 3, its concentration got cut in half.
Yeah.
So that means that should cut the rate in half. So I took this and divided by 2 and I got that. That's why I have the BR2. So the impact of the BR2 should cut the rate in half.
And that determines.
Now we're going to look from there to there at what happens with the NO.
It doubled.
Yeah. Well, no, it went up by 4. That
That
concentration doubled, causing the rate to go up by 4.
Okay.
Yep. So that's how I came up with a 2 order. Go ahead.
Why do you not have to cut the initial of NO in half too?
This? No, we're looking at how the rate is changing from this trial to this trial. So this is getting cut in half, and this is doubling. So because this is first order, we know the order of this one is first. So when you cut that in half, it should cause the rate to get cut in half. And that was what I did. It doesn't mean the other concentration gets cut in half. It's just the rate that gets cut in half. So the order of this doesn't affect the order of that. You have to look at the order as individual. Okay, the order just goes back to what the rate is. Okay, now the last question is D on this one. What did you put for that one? Does it agree or does it not agree? Or is it a consistent mechanism?
No.
The answer is no, it's not a consistent mechanism. Because the experimental rate law we found had an order of 2 for NO. When we look at a mechanism, all we care about is the slow step in the mechanism. In that slow step that I circled, that's the rate determining step. And the rate law, according to that, is rate equals K times whatever is reacting. 1 BR2 and 1 NO. We can always write the rate law given a mechanism. Just find the slow step. It'll always tell you which steps are fast and slow. And then just write how many molecules of each one of the reactants are reacting. In this case, there's just 1 BR2 and 1 NO. That is not consistent with the experimentally determined rate law. So that's not a good mechanism. Yes?
So if there was a 2 coefficient from the NO, then
Yes, that would change the story. That would be a good
so
mechanism.
would we just like, what would we say? Would we just say it's consistent?
Yeah, you'd say that it is consistent. Remember, there's 2 criteria for a mechanism to be valid. Number 1, it's got to reflect the experimentally determined rate law from the slow step. Number 2, the steps have to add together to give the overall balanced equation. I didn't even add them together to see if they added up to the overall balanced equation. I just saw that the slow step did not reflect the correct rate law. We'll do this more tomorrow. This stuff about analyzing a mechanism, we'll spend a lot more time on that tomorrow. So I'm done. We got, what, 13 minutes or so. You can work on the lab.
Analysis.
He's gonna ask you about stupid sig figs.
Is this the recording?
Yeah, it's recording.